Communication is key. Whether you're just starting out or whether you want to get a better in-depth view of how it works, welcome to today's Guide to Modbus Wiring. We're going to be going through an introduction into Modbus and into communication between devices using Modbus, concentrating on Modbus RTU. I'm Anthony Moises and I'm here at Fronius International in Wales. I'm not alone in the studio. I'm also accompanied by my colleague, Michael, and he's going to be looking after the chat today in our webinar. To the side of your screen, if you're in a browser version or in the app, you'll have a questions tab. Feel free to ask your questions there and we'll answer them either directly in writing or we'll come back at the end of today's webinar and we'll answer those questions here live from the studio if they're interesting for more of our viewers. And with that, let's get started looking into Modbus. Today, we're going to be looking through what Modbus actually is, what kind of communication is it, how does it work? To do that, we're going to look at how to wire it. We're going to look at the different criteria for the cables, how to connect those cables as well. While we're doing that, we'll look at the termination. Termination resistance is a key word when it comes to Modbus and getting a clean signal. So we'll look at where to place that termination. We'll also look at shielding, we'll look at interference, we'll see how Modbus is protected against stray signals to make sure that you get the optimum in communication each and every time. And then at the end, we'll come back and give you a summary of all of what we have gone through. Now, in total, it's going to be probably just over half an hour. Maybe we'll manage to keep it a little shorter. If you have questions in between, feel free to ask them anytime. So what is Modbus? Modbus is a communication between two or more devices in the field. It was developed by Modicon in the late 70s, 1979, for Modbus RTU, so a remote terminal unit. That was a communication protocol for one master device at the time to communicate with several slave devices. So one master could demand data from those slave devices in the field and can also send them commands remotely over a considerable distance and also have several connected in series. Now today, most Modbus systems, including ours, are based on RS485. So we're going to concentrate on those aspects. We're going to have that kind of architecture as well. So what does Modbus actually consist of? What is this typology, this infrastructure that we actually need? The core component are two cables that run parallel to each other. They're twisted, and we have a plus and a minus data. Now on this line, we have equal but opposite signals that are sent, and then at the other end, they're analyzed to make sure that they match. So by using these two cables together, this plus and this minus, we get a good, strong offset signal. The fact that they're twisted is also going to be important because that gives us additional shielding against interference and we can't get mixed up. We're using quite a few cables or wires when we're connecting Modbus together. In addition to this pair of cables, this plus and minus twisted pair, we also have a ground wire. Now this ground wire is a contrast basically so that we have something to measure this plus and minus against, and that's a common ground between both of the units that we're trying to have in communication. Between the plus and minus at the ends of our line, we're also going to have to make sure that the signals don't cross over. And to do that, at the end, we're going to put in a termination resistance. Now, in our case, this is going to be 120 ohm termination resistance between plus and minus at the end of every Modbus line. What that termination resistance does is it swallows stray signals, it swallows any signals that are excessive, so usually interference, etc., so it does not get transferred from a plus onto a minus signal or misinterpreted at the other end. You'll often hear of Modbus and echoes or reflections. That is usually when there is no termination resistance and those stray signals come back and are misinterpreted as data, or they end up corrupting another signal. So a very important part here, the termination resistance at the end of our serial connection. Another way of protecting our signal is to make sure we don't get any signals transferred to it by induction. So particularly if we have communication lines that are next to a power line, we could have stray signals that are transferred. And to make sure that doesn't happen, we add a shield. And that shield acts as an aerial. It catches all of that stray interference, and we put it into a harmless shield earthing point at one end of the line. We're making sure it's only one end so we don't have a difference in potential, but we have to make sure that it is connected to an earth, so to a shield contact, to make sure that those stray signals are taken harmlessly away and never reach our data lines. And that already shows us what kind of cable we're going to need. So we're going to start off by making sure that it is a shielded cable. There are several forms of shielding. So it could be an S type, so a shielded type with a woven shielding. It could be an F type with a foil shielding. It could go around all of these cable pairs, or it could go around individual cable pairs. So whether you're using an SSTP or an FSTP or an SFTP, it doesn't particularly matter. The main thing we want to make sure is that we have some form of shielding, preferably around all of them, but definitely around the individual pairs. So you want to avoid a UTP, an unshielded cable with unshielded twisted pairs. And that brings us on to the next part, the twisted pairs. So if we're using most of our communication cables, these are always going to consist of 4 twisted pairs. Now those 4 twisted pairs comprise 8 wires in total, always a colored wire and a corresponding white that is twisted with it. Now that'll be important when we come to the schematics. You saw beforehand that we had a colored line, in that case an orange line, and a dotted orange line or an interrupted orange line. That would be a fully blocked color, the orange wire, and its corresponding white is then the white and orange. So we have to have twisted pairs. Note that these are differently twisted. They have a different twist number to them, and that also helps make sure that data from one twisted pair is not transferred to the other as easily. So again, another form of protection, another form of shielding from stray signals. What that gives us then are wires of category 5 or higher. So LAN cables category 5 or higher. Be aware of the fact that there are some, for example, some cables of type 6, which do not have the right level of shielding. So make sure that you're using a LAN Cat 5, a LAN Cat 7, a 6A, for example, for your data transfers. The total run of that Modbus series can be up to 300 meters. So from one device to the other end of the line, including all the devices in between, we don't want to exceed 300 meters, simply because after that, we would lose too much signal. To make sure that we get that signal at maximum strength, we can use up to 1.5 square millimeter cross-section on those wires with our terminations. You could also start as low as 0.05 square mil. You're working with very fine wires then. So finding a good balance between the length you need and the cross-section is important. Also important to note, please use copper cables and copper wires, not aluminium coated or copper coated aluminium rather, but stick to full copper wires so that they really can manage the full signal. So carrying that information over, we've seen that we're using LAN Cat 5 cables or higher, and let's have a look at which of those strands we're going to use. As we see here, we have a brown wire forming the ground. That's the ground wire, the brown wire of that brown and white pair. We're simply ignoring the white here and using that brown to connect both ends. We're then going to use the orange wire for our Modbus minus or data minus here, and the corresponding white, so the white wire that it is twisted in a pair with, for our plus, and that is this orange and white dotted line here. We also have a contact for the shield here. This wire, or this cable has a wire incorporated so we can attach the shield. If that were not the case, then we could always create a contact. We could twist the foil and put a ferrule on it, for example, and connect that then to our shield contact. Or here we can use this contacting wire, wrap it on the shield, and then connect that to our shield contact. With that, we see why we have to use those cables and how they work and which pairs we're using. The other pairs can, of course, be used for other lines. They can be used for other communication methods. They could be used here for our digital in and out controls, for instance, if one wanted to. So how do we connect the ends? There are several ways that you could connect a Modbus line. Now, as it's an RS-45, you can use a standard Ethernet plug at one end. It's the same topology. We also have screw terminals where we can clamp down on the cables. If we're connecting several wires together, then we would twist them together and then insert them, or insert them into a ferrule and then clamp down on them. There are also many proprietary plugs where we simply push the end of the wires in, or again, use ferrules for that. Main thing is we're creating a strong positive contact between those wires and the contact point. So what would a wiring diagram look like? If we're connecting, for instance, our smart meter, then we saw beforehand we have pins 8, 9, and 10 that we are connecting. We're connecting those with screw down terminals. We've got our Modbus plus on 8, so that's the white corresponding wire for the orange. 9 is the minus line, that's the strong orange wire, and then on 10 we'd have our ground on the Fronius smart meter. On the inverter, we then have labeled contacts again. We've got M1 minus and M1 plus, corresponding wires pushed into that plug there, and also the ground pushed into the plug. We're connecting the shield, which is around all 3 wires or around the entire cable, to one end, and in this case we have a shield contact already provided on the inverter plug, so we'll simply insert it there. Putting that together, we then have a contact where we have our full smart meter and we have our plug then on the data pilot on the inverter. We've already got the wires in place, but there's something missing. We've got wires, we've got a shield, we're still missing a termination resistance. And that 120 ohm termination resistance has to go at the ends of this communication. If we look at the smart meter, we're going to place that between 7 and 9. But we don't have to place the resistor. There's already a resistor integrated into the device. All we have to do is activate it. And to activate it, what we'll do is we will put in a jumper. We'll put in a cable bridge, if you like, between 7 and 9 so that the signal goes via that resistor internally. Having completed it at the smart meter end, let's have a look at how we would do it at the inverter. Now, on the inverter, we have a sliding dip switch, which we can activate. It has a 0 and a 1. 0 means that the termination is deactivated. When the switch is on 1, it is activated. We have 2 of those switches. One is for M0 and one is for M1. The difference between the two, we're controlling the termination resistance for those individual contacts on our plug. Note that on the plug, we have an M1 and an M0 as well. Any Modbus line, a serial line that is connected to that M1 side, and we want to terminate it at the inverter, we'll have to make sure that it is on for M1. We'll come back to that later when we look at other serial connections involving the inverter. But important to note here that we have these 2 switches for the 2 individual Modbus lines that could go in here. As default on the inverter, this switch is activated for both M0 and M1. If you're in doubt, switch it off, switch it on, and make sure that that contact is solid. So we have a contact established between our 2 devices. We have established a contact between our smart meter and our inverter. We have 2 wires, it's a twisted pair. We've connected them correctly. We have a ground that's connected correctly at both ends. We have added our termination resistance at both ends, and we have a shield in place. That is how we would connect just 2 devices using Modbus RTU. But now let's look at what happens if we connect multiple devices. Most of the principles remain the same, but we will have to be aware of one key element. We need our wiring, so we still need our twisted pair between the 2 devices, or between all the devices. We still need our ground between all the devices, and we still need a shield. The shield is also only connected at one end of each line. So we'll make sure that we don't connect it to all the devices. What happens if we add a termination resistance as we learned it before? Well, we'd have a good communication between the first 2 devices, but then the signal would be swallowed. It would try to go through the resistor and it would get lost. So what do? Logically, we want that termination resistance at the end, but we don't want to lose the signal in the middle. Logical solution, let's remove that termination resistance from all the devices that are in the line and only leave a termination resistance at the devices at each end of our serial connection. In other words, if we want to connect our inverter to several smart meters, we can do that. That's no problem. We'll put a termination resistance at the inverter, the beginning of the line. We'll put a termination resistance at the end, at the far end, so at the last of the smart meters that we have connected in this Modbus series. But all these smart meters in the middle don't have that jumper in, they don't have that activating wire bridge. We have not activated the resistance on these devices. The same principle applies even if we're not just using smart meters. Obviously, if we're connecting a battery or some other device in between, we're still making sure that the resistance is not active on the battery. We have an active resistance for the inverter. We have an active resistance on the smart meter here, but not for the battery. Even though we could activate it on the battery, we have a dip switch there as well. But in this case, we do not have to. Making things slightly more complicated, we can also have 2 Modbus series, and we can switch those differently. We said we have 2 switches for the Modbus termination on the inverter, one for M0 and one for M1. Now these are completely separate Modbus series. We could switch Modbus 0, M0 termination on and have this line on the left-hand side between the ohm pilot, where we can again use a dip switch to activate the resistance, then include a smart meter, a battery, etc. on the way to the inverter, and terminate that resistance at the inverter again. On the second line, on M1 here, we could put the inverter in the line. It could be one of the devices in series, but not at the end. So here we have one smart meter which is at the end of the line. That has a termination resistance. We then go via the inverter to the other smart meters. And again, the smart meter at the far end of the line has a termination resistance. In this case, take a guess what we do with the M1 resistance in the inverter. It is switched off, obviously. We switch that dip switch to 0 to deactivate it so that the signal can pass along the entire length of the line. While you're looking at this schematic, you'll note that we have 4 smart meters on M1, but we only have 3 devices here connected to M0. To make sure that we have an optimum data transfer with Fronius devices, we limit the number of Modbus participants per Modbus line to an inverter and 4 other devices, such as smart meters or ohm pilots. That way we can make sure there is plenty of capacity on the line for that data transfer to take place. If we add a battery, then there's even more data transfer between the inverter and the battery. They're in constant communication with each other. And so we reduce that number by 1. The battery counts, if you like, for 2 smart meters or for an ohm pilot and a smart meter. so we make sure we only add a maximum of 2 other participants to that Modbus line. So we'll make sure we set the termination resistance. We'll make sure we always know which position our different devices are in, and we'll make sure we don't have too many devices connected on one line, and try, if you can, to even balance the number if you have the availability of using 2 lines, particularly if they're different in geographical location, but also if you're dealing with a high number, if you're 3 or 4 participants on a line already, consider whether you're going to use the second line if it's a viable possibility from an economic point of view. If we have several participants, then we're going to have an additional complication. We said we have a master or a client device in our Modbus setup. But how does the master or the client know which server or slave it is communicating with? We need a Modbus address. Now, we have several Modbus addresses already predefined. So the OwnPilot has a predefined Modbus address. The battery has a predefined Modbus address. We don't have to worry about the inverter either. The only thing we're going to determine is different smart meters. So if we're adding multiple smart meters to a system, we're going to have to pay attention to which of those has which address. Now, the primary meter is going to have Modbus address 1, and we'll have to assign different unique addresses to the other participants, to the other smart meters. In this case, 2, 3, 4, and 5 would be secondary smart meters. So let's look at how we do that and how we choose which addresses to designate. The primary meter is always going to be given Modbus address 1. Now, you don't have to change anything here. 1 is the default. 1 is the address that they are issued from the factory with. If you're only installing 1 smart meter, you don't have to worry about the Modbus address at all. You just simply install it, and the inverter will take that over as being the primary smart meter that should be at the feed-in point. This is going to be the smart meter that gives the inverter information on surplus in the entire system and can therefore optimize any load management settings. As soon as we add a second smart meter, this is going to be a secondary smart meter as it's recognized by the system. This can either be a producer smart meter or it can be in a load line monitoring how much electricity or how much energy one load uses or a circuit uses. But these are going to need a different Modbus address. We don't want them to be in conflict with that primary meter. The signals will go astray, we won't get proper communication. So here we have to change from 1. If we're adding more than 1 secondary smart meter, we're also going to have to make sure that those don't have the same address. So we're going to make sure that every number only occurs once. How do we do that? We have to go into the settings on the smart meter here first. So we're going to press enter on the smart meter to enter the menu. We're going to navigate to P1, which is near the beginning, and we'll give it the code 2633 and confirm that code. So you're going to use the up and down buttons to enter each digit, press enter briefly for it to accept that digit and move on, and then we'll enter that password, the 2633. Navigate to page 14 and press enter for 2 seconds to say that you want to edit this page. We'll then set the new address. Now, determine which address you need, whether it's 2, whether it's 3, whether it's 4. You can go up to 14. We have a reserved range above 14, which is where our pre-designated Modbus addresses are. So 1 to 14 are available here. Remember, 1 is your primary smart meter. So if you're programming here, you'll probably start at 2. And again, confirm those digits using enter. And then we're going to navigate to page 18, press enter for 2 seconds again to leave the menu. After we've set up the smart meter, we're going to connect to the inverter. And on the inverter, either we're in the commissioning process or we can go in after the fact and still add components. And in this step where we're adding components, that's step 2 in the configuration process, we're going to first add a primary smart meter. Now, as we go to add component, smart meter will automatically be given Modbus address 1 as a suggestion. We select Modbus smart meter RTU, and it will first suggest it as at grid connection point. At this point, all we have to do is click on add, and it's already set up. Modbus address 1 is on the primary smart meter. We didn't reset that. Modbus address 1 came up as a suggestion on the inverter interface. We don't have to change that either. We simply add the component. When it comes to the second smart meter, we will, of course, have to change something. As soon as we go to add component and want to add another smart meter, again, selecting a smart meter RTU here, it now gives us a different Modbus address. Now, it'll suggest 2 to start with, but you can change that depending on what you programmed into the smart meter when you were setting that up. Make sure that they match. I suggest always keeping documentation as you go through and keeping a logical plan of which smart meter is placed where. And the name you assign it here is also the name that you'll be able to see in the monitoring later on. But it is all tied together by this unique Modbus address. Click add, and then you'll have the component added to the master device, to the client, namely our inverter. And then the inverter can manage the data transfer with that smart meter. So we've seen all the elements that we need to observe here, and we've heard a few additional bits of information on what could cause problems. So let's go through a quick checklist of what it is that could cause problems and how to do it right to avoid those problems in the first place. Let's start by making sure that all the necessary wires are connected. So if we make sure that we have a good contact, they're well placed, we've used ferrules where necessary, or made sure that we've screwed down our terminals, then we should have a good positive contact. You can always measure between the 2 points if you're not sure. Have you used the correct wires? So have you made sure that you have used a twisted pair? Have you used the correct white wire, the corresponding white of that twisted pair, and not got them muddled up somehow? That way you should make sure that you've already avoided one of the major problems. The next biggest issue is going to be setting the termination resistance. Now, particularly if we're going into an already existing system, we're upgrading a system, we're adding to it, then it is particularly easy to overlook termination resistance that was already placed. We have to make sure that that is removed if we are extending the Modbus line. And also, when you're putting in new devices, make sure you put that termination resistance in. It's not just putting it in the middle that's a problem, it's leaving it out at the end. So always check your termination resistance along the line. And if you're not sure, you can check that the resistance is active by measuring on either end of that resistance as well. Did you connect the shield at one end? Now, these are problems that you will not be able to tell exist initially. Now, problems with shielding, they occur at strange times when you switch on a load, when suddenly there is more energy flowing on a wire parallel to your data communication line. And these are very hard to analyze. So start off by connecting that shield. Make sure that you do not leave that shield connected at both ends. Otherwise, you're potentially creating a potential difference. But do make sure it's connected at one end to act as an aerial and get rid of those stray signals from the get-go. If you have problems finding a secondary smart meter or finding smart meters in general, make sure that you have set the correct Modbus address on the device itself. So make sure that you've gone in and edited from address 1 on any smart meters that are in a secondary position. And also, quite commonly, the devices are not added to the inverter itself. So always remember to go in and add those components to the inverter interface so that the master or the client device knows to look for those devices and knows to send commands or to analyze data. I hope that that was able to answer many of your questions, giving you a quick overview of Modbus and how it works and how to connect it, avoiding those little problems that often come up and cause major issues further down the road. I'm going to ask my colleague Michael quickly whether he has any questions that came up. Yes, we do. No, we don't. We do not. In that case, we'll stay online for a little bit and still answer any questions as they come in, a couple of minutes just in case something comes up. In the meantime, please feel free to have a look at what other webinars we have on offer. There are quite a few interesting ones coming up in the near future. And even if you do not find a webinar that interests you, sign up for another training with us. We have online trainings, face-to-face trainings, if you can come and visit us here in Austria. And otherwise, if you have a problem in the field, please do feel free to look at our YouTube channel, where you will find a great many how-to videos so that you can solve problems in the field in a very short format, and also quite a few webinars like this one, providing you with useful information, making your life that bit easier every day. With that, we'll be switching off the camera, switching off the microphone, staying here to answer your questions for a few more minutes. Have a great day still, and from me, goodbye for now.